talking, one or two more will turn up. Essentially today, at least for the first part of today, we're going to look at this section, surface area. And I think there's 10 questions altogether, which in the big scheme of things is quite small. So that's a good thing. Secondly, most of the questions are pretty straightforward, with perhaps the exception of organising the region that you're going to be integrating over. So let's give you a background to the story. You're going to have a region D on the, could be, typically it would be on the ground, but it could even be floating up as long as it's the same triangle. And this triangle is then projected upwards to a surface Z, Z equals Fxy. And so you can imagine it might be a nice straight triangle, but when you take the points, it becomes a much more triangular shape, but it's got more curves to it, right? Can you imagine? Oh, I don't know. The shadow on the curved flying carpet would be triangular. And what we're going to do is we're going to be finding the area of that curved surface, and it's typically called S. So essentially the question is find the surface, right? Surface area, because we're only interested in the area of that. And when you have a region D being projected onto some surface Z. And the formula for it is as follows. The area of the surface S is found by finding a double triangle. It's going to be in the region D, which is the region on the floor, the XY plane typically, followed by this guy. The square root of the derivative of this with respect to x squared, plus the derivative of that guy with respect to y squared, plus 1, finishing with dA. And dA is your typical dx dy. And you should probably use dx dy when the region on the floor is rectangles, triangles, or things like from y equals x squared to y equals square root of x, right? Distinct regions that you can calculate simply in x and y. And the region dA should sometimes be in polar. And you should really do that when the region D is something to do with circular. So of the 10 questions that we've got, 4 of them are going to end up being dx's and dy's. That's questions 1, 3, 4, 5. And then the other bunch of questions involves something to do with a circular part of it. And so they're going to use the polar coordinate system, r, dr, d theta. And there's one of them where the guy on the bottom isn't on the bottom. He's actually like 3 feet off the bottom. And we'll show you how you tackle that. And it's a one-off question. So without further ado, this is going to be question 1, but let me show you the information where it originally came from in your homework. Right, should be looking at question 1 here. It's not the same as my question 1, in the sense that maybe I didn't draw it quite the same, but the gist of it is here. Do you see the curved surface Z is this blue thing? On the floor, there's a triangle. That triangle is projected up and it meets the surface like this. And our job is to find the area of that curved triangle, right? So the surface area is the area that you would get if you took the floor and projected it up to the surface Z. So far, so good? Right. So let's go back to the question at hand.
So I think my internet's bad because of you're breaking up a lot. I don't know. Is anybody else experiencing that?
I don't know. Is anyone having issues with connection with me?
I'm not.
Maybe just be you, John.
Yeah, I think so. Thank you.
Yeah, give your hamster a bit more cheese, you might learn faster. Okay, so in that question that's now disappeared, the important information is essentially the equation. Oh, if I had a brain, it'd be dangerous. The equation of the surface, which is x squared plus y squared, there it is there, is this guy, the equation of the surface, and the region D. So what we're going to be able to do is find this ugly square root. and the limits of integration. So let's go straight for the region D, and I want to find out its limits of integration. I would think the best way to do this shape would be to scan it along the x-axis this way. And if I scan it along this way, the values of x go from what, -2 to 0? Now, what about the y values? Well, you got this guy and you've got that straight line. So this straight line here, we need to find its equation. It's actually not that difficult. Its slope is 1 and it passes through the origin. So it's basically just y equals x. You're comfortable with that line that makes up the triangle? It's just a y equals x line. I mean, if it was up there, you'd see it better. So we are looking at the region of y from here to here. Now we have a decision. Is it 0 to x or x to 0, right? So one of them is the smaller, and the smaller always goes where my finger is on the left. And one of those two things I mentioned is bigger than the other, and it belongs here on the right. And the orientation of this triangle, do you see the straight line is much lower down? So the y value would be quite negative, and so that would be considered the small guy, and then 0 on that guy. And that is our region D.
Can you point out the straight line with the tip of your pen?
Here. That's the straight line.
Yeah.
You see him? That's the one that's equation y equals x. Now, the formula tells me, okay, that's the limits of integration. Now I need to calculate this ugly guy. Now let's see what it looks like. Since z is 19 plus x squared plus y squared, the derivative of z with respect to x is 2x, and the derivative of z with respect to y is just 2y. And the equation that we're going to be using, I'll do it on this page here now, it's going to be the area of the surface is the integral from y equals x to y equals 0, x equals -2 to x equals 0, the square root of dz by dx squared plus dz by dy squared plus 1. I'm doing the y's first, and then I'm doing the x's. And if you're wondering where did this 1 come from? It's actually dz by dz, which is 1. Okay, we good?
That makes sense.
Now, adding in a little bit more detail, we've got the limits of integration set up, so I don't need to do anything about them. It's now going to be the square root of, if you plug this guy in, you get 2x and then you square it. If you plug this guy in, you get 2y and then you square it, then you add 1. And now we have a dy kind of dx thing going on. And then we just have to look at what we've got and decide is, you know, the techniques that we're going to use to integrate it. And of course, I made an oopsie. Z is 19 plus x plus y squared. That makes this guy here 1, which makes this guy here 1. So now we've got x equals -2 to x equals 0, y equals x to y equals 0, 1 squared, that's 1 as well. So you're going to get 4y squared plus 1 dy dx. Are we good? 1, that guy squared 1. 2y times itself, that guy. Now, having got to this point here, I have just realized, because you don't know sometimes until you do it, that these limits of integration are not going to work well with this function. Because don't I need to integrate the square root of 4y squared plus 1 dy? And can you imagine that is not going to work? Which means then that I have to just change my limits of integration to suit the information. So I didn't know that was going to happen until after we created it. So
Yeah, Thomas has a question. I had the same question as he did.
oh, okay, Thomas. Is it not plus 2? Yes, it is. Right, so what I'm going to have to do here is adapt. Do you know how I decided to do this one that way? I'm now going to change the orientation. So here's the straight line again, looks like that. This is -2, this is -2. This line here is still y equals x. I'm just going to call it x equals y. And now I'm going to do my guy that way. So instead of making the triangle with vertical scanning, I'm now going to do it with horizontal scanning. So let's see how that changes.
Can
Yeah,
you,
John.
if you don't mind, can you tell me the rationale behind your reasoning for changing?
Oh, when I saw that integral, the square root of 4y squared plus 2 dy, and I said, I'm going to have to integrate that with respect to y, I said, I don't want to do that. That's not going to come out nice. Right, that's it. That's the only reason. Now, if that integral was something easy to do, I would have left it alone and kept on going. And sort of, you know when an integral's good and you can know when an integral's bad, and I can look at that one and say it's bad. So if I'm going to do it that way, the orientation's a little bit different. So let's see what we're going to do. Y is going to go from here to here. So that means y is going to be from -2 to 0. And the x's, right? So the x's are going to be from straight line to that guy. And I can see that -2 to the straight line is y. So that's my limits of integration going horizontal. The y value goes from 0 to -2, slightly big. And the x's go from this point, which is -2, to that point, which is a little bit bigger. And that point is the straight line y equals x. But I need it to be written in terms of x equals y, so that's why that's a y.
So do you always go from left to right on the x?
You go from small to big. So on the x's from left to right, and on the y's it's from low to high. So our guy is now going to be the integral from y equals -2 to y equals 0, from x equals -2 to x equals y. That's still the same guy. But the difference is I'm now going to do x before I do y. Now, if you look at this integral and you look at that, this bit's the same. These two are switched, and the limits of integration are quite different because of the orientation. So, to finish this off, I'm going to do the integral from y equals -2 to y equals 0, bracket, bracket, dy. And I'm going to focus on that ugly square root. But that ugly square root with respect to x, when you integrate it, just gives you x times the ugly square root. evaluated at x equals -2 to x equals y. And so I now have y equals -2 to y equals 0. If you plug in y, you get y, the square root of 4y squared plus 2. And if you plug in -2, you get negative, I've lost the guy. Actually, yeah, you plug that guy in, you got -2, 4y squared plus 2, and dy. So at least I got by the first integral, right? If I'm going to do that guy, it's basically going to have to be a u sub. And to do that guy, it's going to have to be a standard integral. So that gives me a chance to show you what's going on. Right, if I stop the sharing, I want to show you some stuff that I have kind of connected to this. Your midterm is going to be on a week today, Monday. And I don't know if you've seen this, but on Canvas, I've put up a whole load of stuff. And with the exception of these two practice ones, all the other things are going to be here. So for instance, the one I was about to do, which is a standard integral one, goes here. And if I go hunting for it, I'm sure I'll find a version of the one I'm looking for. I'm looking for something y squared plus 2. So yeah, it'd be that one. It'd be a version of that one. Now, on Monday, everything else in Canvas will disappear. Everything in WebAssign will disappear. So the only thing you're going to have to work with is what's on this page here. Here is the special Zoom meeting for the midterm. You need to have a camera, and so I can see what you're doing, and you need to have audio so I can talk to you. This one here better not have the midterm exam because I haven't written it yet, right? This is a placeholder for it, and you won't find anything in there until Monday. When you are doing your exam and you've finished, here's the link to upload your work in. You all know how that works. Well, let's just try it out. I'll need to go into student view. Okay, so I've done my exam. I want to show you my working. So I'll click on this. Oh, there's some stuff I don't want. Oh, it's probably, that's right, it's not available yet until 8 p.m. Okay. If it was available, you'd be able to click on File, Upload File, but I forgot to do that, so it is what it is. There's a video on uploading using Microsoft Lens. There's a video how to download your PDF. Now I've got some other little bits and pieces. These two will disappear on the day of the midterm. Here is a practice midterm. Now you got to remember that I did these guys, so be on the lookout for mistakes. If you can find some, shoot me a little email saying, I think question 7C, and I'll check it and fix it for the rest of us. But there's multiple choice questions, 10 of them. And here are section 2 questions, 13 of them. And you have your 3 hours to get your exam done, plus some time to upload it. And if I go back a little bit and I click on this one, here are a whole bunch of questions. That's 20 in total. And here's another bunch of questions. There's bound to be some overlap. I just found whatever I could find, 9. And here are the solutions to all the A questions. Keep going. There's a solution to all the B questions. So hopefully I've given you enough resources there for you to get ready for your midterm, right? So lots of questions. You can find out what you're good at, what you're not so good at, and maybe do some practice. And
Are we gonna have to use any software to solve any of the problems?
no software allowed, so none of the questions will need software. Now, if you
So
have,
Desmo, yeah.
imagine you have a question where I would use Desmos to draw the region D, right? In those questions, I would do it myself, and I'd copy that and put it into the test, so you would see what the thing would look like in Desmos. Right. Oh, excuse me. Now, switch my phone off so we won't get that disturbed. Any questions about that? We're all aware that when our test is going to be, right, which is Monday, and you have 3 hours to complete it. Hopefully you'll do well and you'll be prepared for it.
Are you gonna have a kind of review session, or that's just up to us?
Well, you know, it's a time issue. I mean, you can certainly contact me and we can do a one-on-one. I don't know who needs that information, so I don't really, you know, want to book a time and then you feel obliged to turn up, because you might want to just do your practice on your own in those times. But I mean, if you come across something, we can do a one-off Zoom meeting and I can go over it. Yeah, I won't be available on Saturday because I'm going somewhere with my wife, but I'll be available on and off anytime this week if you come across something. Because I teach during the daytime, I won't be available until, you know, after 2. But as long as you stick to that, you should get me. Okay, let's stop that share and let's do some more questions. Okay, this is a version of question 2. The surface is actually a plane, and its equation looks like that. And the region D is basically a circle and all the points inside it. Now, that information there kind of screams out polar, doesn't it? Right, so what I'm going to do is R goes from 0 to 3, right? Because that's a radius of 3. And it's a complete circle, double check. Yep, it's a complete circle. So it's 0 to 2 pi. And now we've got D. This guy is not any good. This guy is written in a format that's no use to us. It needs to be Z equals a function of X and Y. So all I'm going to do right now is take away a 2x and take away a 4y, and then divide everybody by 2 to get that. So that is the surface in the form that we need it to be. Its equation has to be written as Z equals, because I need to differentiate Z with respect to X and to Y here. So I think we're ready. This one's going to be pretty good. It's going to be R equals 0 to R equals 3. Theta equals 0 to theta equals 2 pi. The square root of. If you differentiate this with respect to X, you just get the number 1 squared. If you differentiate it with respect to Y, you get the number 2 squared plus 1, technically 1 squared. And it's going to be R, theta first, dr, right? And so I have R equals 0 to R equals 3, theta equals 0 to theta equals 2 pi, 4, 5, 6. It's basically the square root of 6r d theta dr. Oh, we lucked out here. Both integrals contain nothing but numbers. And isn't this technically variable separable? So I'm going to do r equals 0 to r equals 3 of the square root of 6r dr times theta equals 0 to theta equals 2 pi. And if everything disappears, you always get a 1 left. This guy is 2 pi. And this guy is a power rule. And we evaluate it at 0 and at 3. So that gets me 9 square root of 6 over 2. Times 2 pi. The 2's cancel. And in the big scheme of things, that is quite a nice answer. And yep, it's the right answer. That was a little bit in the quick side, but I think it was pretty smooth, right? It had a nice flow to it. There wasn't too much weird things going on. Needed to figure out what Z was in terms of X and Y so that we could get this bit here, which turned out to be numbers, which was great. Because it was a circle, it seemed reasonable that polar would be a more efficient form than to try and leave it as X's and Y's, which you typically should do, right? Circles are polar, straight line stuff, or rectangles, triangles, etc. They tend to be X, Y's. Are we good with that one? Any questions? Okay. Now, next one on our list is a version of 3. Again, it's one of these equations of a plane. But this time, it's in the first octant. So, if I rearrange this guy, Z equals 10, take away 5x, take away 2y, and that's good. What's not at all obvious is what is the shape that we're going to have on the floor that's going to be projected upwards and meet this guy. So I'm now going to do a sketch of this situation. If you know the equation of a plane and you want to know where it crosses the X, the Y, and the Z axis, that way it'll be in the first octant, you simply do this. It crosses the X axis at 2. You basically make these two guys 0 and you get the X one. If you make these two 0, can you see that Y equals 5? And then Z equals 10. So if I was going to try and draw what this shape looked like, can you see it looks like one of those tetrahedron guys? So far, so good. Now, the region D is this triangle guy on the floor. So I'm going to rearrange the orientation of it. So the X is 2 and the Y is, that's a 5. That's my region D. This sloping bit is actually that guy. And we're trying to find essentially the area of this bit. So I have all the pieces, I just haven't set up my limits of integration. In this question, couldn't I do X equals 0 to 2 and go vertical? Can I also do Y goes from 0 to 5 and go horizontal? If I choose the wrong one, won't I have to switch the order of integration to suit the math? But I'm pretty sure this time that scanning vertically is going to work. So when you scan vertically, the X's have numbers and the Y's go from 0 to that straight line. And that straight line has an equation which I'm now about to find. Anybody want to tell me the slope of that straight line? Just by rise over run and looking at it. What
5
is
halves.
this? Say again?
5 halves.
Yeah. And would you agree it's negative because it's sloping downwards?
Yeah, plus Thomas pointed that out. So
Right. And also, isn't it y-intercept 5? So the equation is -5 upon 2x add 5. Are we comfortable about the equation of that sloping line? So that's what goes here. Okay, now we have everything that we need. We can apply this formula. The area of the surface is going to be the integral from x equals 0 to 2, the integral of y equals 0 to that ugly straight line equation that we just found, the square root of, well, if you differentiate z with respect to x, you get -5. If you differentiate y or z with respect to y, you get -2 plus a 1, do a dy, do a dx. Next line would look something like this. (2534). It's just a number. The square root of 34 dy dx. So it's going to be the integral from x equals 0 to x equals 2 of that guy, which is square root of 34 y, evaluated at y equals 0 to y equals -5 upon 2x add 5. So that's going to get me x equals 0 to x equals 2. And let's plug it in. You're going to get the square root of 34 times this guy minus 0, so I don't care. Are we comfortable with where we are right now? I'll get a chat, so let's see what that says. Yep, okay. Now, if something's a constant and you just don't want to deal with it, you can actually pull it out. I don't know if that's any benefit, but it just kind of makes life a little bit easier, I think. Okay, add 1 to the power, divide by the new power. 5 gets you 5x from 0 to 2. Plug in 2 here, you get 4, so that's -5. Plug in 2 here, you get what, 10. Take away a whole load of zeros. And 5 square root of 34. And nobody noticed something, which I just noticed the other now. 25, 1, and 4 make this 30. Good news is it doesn't really change any of the math that's important. Yeah. Gotta keep your eyes on me. There we go. So the area of this sloping piece, the one that's coming down like this, it's basically a triangle, would be that number there. And that's considered the surface area in this question. Okay. I'm going to set up some, but not do them. So in this next question, we're given a surface written in that format. And we're told that the region D is the triangle formed by joining these 3 points together. Okay, so the region is a triangle and the surface is given in this ugly format. So this guy here needs to be written as Z. So add an x squared to both sides, take away 2y from both sides. Divide everybody by 4. And that is the form that Z needs to be written in. Now that region D is going to be a triangle, 0, 0, 2, 0, and 2, 4. That's the region D. Okay, do you want me to build this region by vertical scanning or horizontal scanning? And actually it doesn't matter because both work, but which one would you like me to do? Vertical scanning or horizontal scanning?
Vertical.
Okay, so we go vertical, it's this guy. And if you go vertical, then the x's go from 0 to 2 because you're scanning like this. And the y's go from 0, which is the easy one, to the equation of this line. And the equation of this line is not that bad because if you do rise over run, it's just y equals 2x. Now we should be able to set it up, and at this point I'll stop. It's going to be the integral from x equals 0 to x equals 2, the integral from y equals 0 to y equals 2x, and the square root. Well, if you differentiate this guy with respect to x, you get a half x that you then square, and this guy, you get negative a half, and then you square it, plus 1, and then you're going to do a dy and a dx. Okay, that guy is going to be a quarter x squared and plus 5/4. And I know that looks really ugly, but if you integrate it with respect to y, your next line, you will have a guy that looks something like this. That's what the next integral would look like. How are we going to integrate this guy with respect to x? What method should we use?
U sub.
Yeah, and the u sub will be this ugly guy in the middle and everybody's happy. Okay, next one, I'm just, oh, by the way, that was 4. Next one, I'm only going to set up, which is 5. And we have an x squared plus z squared equals 100. And we're told that it's a rectangle and the vertices are 0, 0, 5, 0, 0, 5, and finally 5, 5. And I guess if I draw the picture of it. And that's good news. Because it's a square or a rectangle, it's always good news because the limits of integration are both numbers. So far, so good. Now, this fella here has to be rewritten as z equals So that means it has to become that guy. Are we good? Right. Has to become that guy. Now, we got all the pieces. So let's set up the integral for the surface area. I'm going to go y equals 0 to y equals 5. I'm going to do x equals 0 to x equals 5. Square root of, and I'm going to do a dx and a dy. Right, now this fella here is a bit messy. The good news is that that guy is 0 because this thing has no y's in it. So I know I'm going to have plus a 0 squared plus a 1, right, which is that guy. That's my general formula. Which is that guy squared plus 1. The problem is this fella here needs to get differentiated. So I'm going to call it 100 take away x squared to the half. Now when I differentiate this guy, it's going to be 1/2 100 take away x squared to the -1/2 times -2x, which means that I'm going to get a -x 100 minus x squared to -1/2. If I'd planned ahead, I'd have more room. And that's going to be -x over the square root of 100 minus x squared. Okay, so in here, this guy gets squared. Right, I won't write all the limits because I want to focus on this a little bit more. I didn't realize it was going to be quite as ugly. That guy is x squared over 100 take away x squared plus 1. Are we good? Now, you don't know what you're going to get until you get to this point, and then you have to really work hard on what on earth am I going to do with this integral, because the way it's written right now is not going to cut it. It's just not going to work. It's bad enough being inside the square root, but having two pieces is just asking for trouble. So I'm about to do some math to this guy. Are you okay with the number 1 being turned into this fraction so I could add it to that guy? Now, algebraically then, these combine and you now get the square root of 100 all over 100 take away x squared dx dy. The square of 100 gives you 10 over the square root of 100 take away x squared dx dy. And at that point, it's a standard integral. It's actually a version of the inverse sine. And where will I find it? You will find it in that list of standard integrals. Do you know that one, John, you were showing us, which is all the guys at the back of the book?
Yeah.
Right. Canvas, I've just taken a copy of those pages and put them all in Canvas so it's easy to find. So you just need to go hunting. It'll probably be something like this. It'll be a U, they always like U, so it'll be something like that. And I believe the answer is 1 over A, the inverse sine of U over A. So in our case, that would be 1/10 of the inverse tan of a 10th x, and then you're good to go. Let's check it. Oh, I was right, it is. Good. Right, this is 6 coming up. at least the equation is good to go. And the region is the bit that's between that circle and that circle. Okay, just looking at the information, this is the region D, and this is Z. Just looking at that information, why do I know I'm going to go polar?
Because you got two circles with you both have radiuses, and you're gonna find out.
Right, and the radius are what, 4 and 5, and so the
Yep.
region we're talking about is a donut. So that's telling me that R is going to go from 45. Just check its whole circle, it is. And theta is going to go from 0 to 2 pi. So that kind of lends itself, doesn't it, to polar. Right. So, ready to go? The area of the surface is going to be, no particular order, R equals 45. Theta equals 0 to 2 pi. Square root of R dr d theta. Right. If you differentiate this with respect to x, you get negative 2x and you square it. This guy, you get 2y and you square it plus 1. And so you're going to get these double integrals. And it's going to be 4x squared plus 4y squared plus 1 times r dr d theta. Okay, everybody needs to turn into r's and thetas. Forget about that one for a minute. What does 4x squared plus 4y squared turn into in polar form? Okay, what does x squared plus y squared turn into?
R squared cosine.
So won't 4 of them get you 4r squared? Yeah. So square root of 4r squared plus 1 times an r, a dr, and a d theta. Well, we are good to go because it's variable separable. And I'll put the r at the front because it looks nicer. There is all the r's times theta goes from 0 to 2 pi. And if you have everybody used up, you get 1. So that guy is 2 pi. How are you going to integrate that guy?
Same as before.
Same way as before, use up. Question 7's a kind of carbon copy of that one with slightly different numbers. Let's move on to 8 then. And question 8, Z is nice.
You mind
And
if
the
I
region,
ask you a question real quick?
sure.
You know, off topic. So
Okay.
we just took a test 4, right?
Yes.
Do you ever like take time to go over those tests at all, or
Yes.
you
So
do?
every time you look at that test, I did it, for instance, on this one, you'll find that most of you got more points than WebAssign gave you because I go over them and I see, okay, WebAssign just matches 0 regardless of how close to the right answer is. So I just go and I look at them, and simple mistakes like there's 3 bits and you got 2 of the bits right and 1 of the bits wrong. Right, so the right answer might be in e squared plus e minus 7, and you got e squared plus e minus 4 or something. Then I know from the first 2 that you must have been doing the thing right, because you wouldn't just get those things randomly. And I add points on. So when you look at your score, at least when I do it, there's a little asterisk and it tells me how much I've added. In your case, you might just have the final total with a little asterisk on it, or it might just be a final total. I don't know how you see it. But I do go through them every time. I went through this one the same way.
Yeah.
Now, The region is a circle, and I was just checking there, it's a whole circle, which is good news. And here is Z. So this one is going to be a circle of radius 8, and since it's the whole circle, there's D again, right? That was clean. And this guy is good to go. Now, what might happen is the integral becomes a bit ugly, but we'll check that in a minute and see what we end up with. It might not be as bad as I think it's going to be, but we'll see. Okay, if you differentiate this guy with respect to x, you get y squared. If you differentiate it with respect to y, you get x squared plus 1. And guess what? It's nice. You're going to get an r equals 0 to r equals 8. You're going to get a theta equals 0 to theta equals 2 pi. That's an r squared. So it's going to be an r, the square root of r squared plus 1. There's going to be a d theta and a dr. Can you see another variable separable? And off you go. Right, this guy dr with these limits and a single 1 for the theta. Not unlike this one, right? Very similar. Any questions? Now, the final one in these is a little bit different. Well, I've got the answer here, so let's show you the question at least. So this is question 10. Oh, come on, it's taking its time to update. Yeah, I think it's updated now. Yes, it has. Okay. Now, what makes this question just a tiny bit different than almost everything we've done is this bit here. Normally, don't you find the exact value, which means you have to integrate it, you have to square root of 6's and e to the 4 and weird stuff, right? Because we want precise. If a question ever says to 2 decimal places, 4 decimal places, whatever, that almost always means that the integral that you're going to get, or at least one of the integrals you're going to get, is too difficult or too ugly to do, in which case you're just going to do it as a calculation, right? So that's the kind of word of warning that's coming out here. Z is the cosine of x squared plus y squared. And the region is basically a circle. X squared plus y squared is 36. They describe it as a cylinder because it's a circle going upwards to meet the surface. So if you're wondering why that's called a cylinder, that's essentially the reason. So since that's region D, I'm going to go polar again. 0 to 6, 0 to 2 pi, and I should be able to set up the integral. It's going to be the integral, I don't know, I'll put theta first just to be different. Right, if you find the derivative of this guy here with respect to x, it's not very nice. Here goes. You get negative the sine of x squared plus y squared times the derivative of the inside function with respect to x, which is another 2x. So you end up with negative 2x, the sine of x squared plus y squared. So that's going to go here. Negative 2x, the sine of x squared plus y squared, all squared. And if you do it with the other guy, you get almost the same thing, but negative 2y, the sine of x squared plus y squared, all squared, plus a 1. So I'm going to have these two integrals. And I'm going to have this guy squared. And this guy squared is 4x squared sine squared of x squared plus y squared plus 4y squared, same thing, and add a 1. Now I can combine these two guys together a little bit at least, and I'm going to get 4, let's say the big square root, 4 sine squared x squared plus y squared times an x squared plus a y squared with an added 1. And now if I convert to polar, I get 4 times sine squared of r squared times r squared, which I'll put here, plus 1 times r dr d theta. Now you look at that integral, there's no way you're ever going to get a u sub or any other standard technique. So that means you're going to find the integral from r equals 0 to r equals 6 of this ugly expression. And times 1, I'll tag on a 2 pi. So how am I going to get that fella done? Well, I'm going to use a calculator. So I'm going to nip over now and just remind you how you get areas under curves using a calculator. Now, the first thing you do is you type in y equals, and you just pretend that r is x, because you don't have an r button. So it's x, the square root of 4 x squared. And to get sine squared, I'll need to do a bracket. Sine of r squared, so that's x squared. Close that bracket and then square it. So that's what 4r squared all squared looks like. And last but not least, add a 1. So that's essentially the same equation that I had with all the r's in it. I've just turned all the r's into x's. I'm now going to go to the window, and it's going to be from r equals 0, so that's x0, to r equals 6, which is that guy. And I'm going to just hit graph, and I should be able to do zoom to fit actually. It's probably nicer. Zoom 0, zoom to fit. Okay, took a few minutes, and whoa, what a weird looking function. It looks like a bouncing ball in reverse. Okay, so the integral that we're trying to do is the area under that blue zigzag curve. So what I now do to finish is blue button, calc, option number 7. The lower level is 0, enter, and the upper level is 6, enter. I'm assuming I hit enter again. Well, if I wait long enough, it will work. Come on. Don't tell me I broke you. That wouldn't be nice. Oh, I've got 2 versions. There we go. Try that again in case for some reason Oh no, it's calculating. It's just taking a heck of a long time. can you trust me? If you wait long enough, it'll tell you the answer and you're good to go. Oh, and then remember, and let's pretend I know what the answer is, which I don't. Let's just pretend that that horrible mess ended up being 42 times 2 pi. You would then go 42 times 2 pi and you'd get, you know, whatever it is, 201.3456. And whatever the real number is, that's what you would do. So I think my emulator, pardon me, I think my emulator just had a hard time of it. Hey, I can tell you the answer now. I just wasn't patient. There. Can you see the answer happens to be 34.71632. You see it very small writing down there. So if you take that answer, which is 34.71632, and you multiply it by the 2 pi that we had, then the final answer is 218.1291 to 4 decimal places. So did get the answer. Cool. How are we doing? Okay with that last one? Right. Got this guy, was that amount. Times it by 2 pi. That's your answer to 4 decimal places.
Well, you're firing on all cylinders tonight.
I'm not sure if I am. I hope I am, but who knows who me. Well, there's only one guy left, and it's question 9. So let's get this guy out of the way, and then we can start our next section. The equation that, or the surface they're talking about, is this guy. And they tell us it lies above z equals 3. So we're trying to find the surface area of this shape that lies above z equals 3. So if you imagine this guy as a sphere, the radius is 5, agreed? Now, if you have a plane z equals 3, it's basically at a height, right, of 3. When that guy cuts this sphere, do you see that you get a piece of the sphere? You can imagine you got an orange, but you didn't cut it through the middle, right? You cut it 2 inches above the middle. Wouldn't you have a little baby, not half a sphere, but you'd have a shape that looks more like that guy, right? That's the surface we're going to calculate. Okay, that's the guy that we need to calculate. So this one requires us to adapt to a slightly different situation. And the first thing I'm going to get this thing going, right, is to realize that this purple circle is not the floor, right? It's actually 3 units above the floor because it's z equals 3. So the region, that's this region here, the sphere. If you put z equals 3 in, what you're finding is that circle. That's essentially D. Do you see it was hidden? See, if they'd said z equals 1, wouldn't I put z equals 1 here and I get a different circle? Could you imagine taking a sphere and slicing it at various heights? Don't you end up with different size circles? So I'm finding out what circle you would get if you sliced it at z equals 3 and it ends up being that circle. That guy is our D. Now, what's the equation going to be? Well, the surface is still this guy. So it's going to be z squared is 25 take away x squared, take away y squared. And that makes z this ugly square root. And so I have everything that I need to set up the surface integral. So the region D is a circle, radius 4. It's the whole circle. So that's that guy done. Z is this fella. So we're pretty much ready to go. The integral from theta equals 0 to 2 pi, r equals 0 to 4, the square root of a whole load of stuff, r dr d theta. And then it gets ugly. I need to differentiate this with respect to x and then square it. This guy with respect to y and then square it and add a 1 and hopefully get something that is reasonably doable, right, as a solution. So I need to just spend a little bit of time working on the pieces. Z is going to be 25 take away x squared, take away y squared to the half. The derivative of z with respect to x is going to be 1/2 this guy to the power of -1/2 times the derivative of the inside function, which is this guy. So it's very similar to one of the earlier questions. Looks like that, which I'm now going to rewrite in its style points format. And while I'm at it, I might as well square it. Get a positive answer. Right, looks like that. And if I want to do dz by dy, I can just use symmetry. Okay, so that's the derivative of z with respect to x squared. That's the derivative of z with respect to y squared. Technically, I'm going to add a +1. So let's do that as well. That guy squared plus that guy squared +1. Is that guy plus this guy. +1. And I want these to be combined into a single fella. So it's going to be an x squared plus a y squared. And I'm going to call this one that guy over himself. So you're going to get +25 minus x squared minus y squared all over 25 take away x squared, take away y squared. And that becomes 25 over 25 take away x squared, take away y squared. So that's what the ugly square root thing looks like. So back to our question. It's going to be, where are you? Yeah. It's going to be, well, actually, since I've got this thing all set up, I'll use it. It's going to be 25 over 25 take away x squared, take away y squared, and this guy. That guy gets you 5. That guy gets you the square root of 25. Minus x squared minus y squared gets me that. Times r dr d theta. And then we get really lucky. Evidently my dog is unhappy about something. Look at this guy. Right, that is actually not that bad. Secondly, it's variable separable. So I'm going to have a 0 to 2 pi 1d theta. And then I'm going to have an integral from 0 to 4, this guy. And by the way, this guy is not an issue. Isn't it just another u sub and off you go? So 2 pi times whatever that is, and you're done. We are finished. We did pretty much every version I can think of. Some to the end, at least a fair number. We're finished. So how to calculate surface areas. Any questions before we move on? Last chance? Nothing? Okay. I'm going to nip over and start our final stuff. Got about, what, 40 minutes, so we can get some good stuff done in that time. And where are we? Oh, here we go. And the last section is going to be section 15.6, which has a very uninspiring heading. It's triple integrals. Right, we've done double integrals. So you can imagine that if you can do an integral followed by a second integral, right, a double integral, there's no reason in the world why you can't have triple integrals. And what do they look like? Well, let's show you one. X equals 1 to x equals 2, y equals 0 to y equals 1, z equals 3 to z equals 5. So you'll have three integral symbols. One will be the limits of x, the second will be limits of y, and the third will be limits of z. This is the simplest situation where everybody is numbers, which is the ones you like. Then you'll have some function of x, y, z. And then we finish with, in not a dv, a dA, but we finish with a guy that's typically called dv. And dv will be, at least as far as we're concerned right now, some version of that guy, right? dx, dy, dz. Now, when you are finding a triple integral, it's a little bit more complicated to describe what you're doing, but we can just about do it, at least when it's a triple integral. I want you to imagine that f, x, y, z represents a blob, a three-dimensional blob, right? If it's a sphere, that's nice. But can you imagine it could be just a asteroid-looking shape, right? A nice smooth asteroid, right? With an egg shape to it. That's essentially the guy that we've got. Now, it's described by the limits of integration. So actually, in this case, wouldn't that just be a cube floating in space, right? A cuboid. But can you imagine if you made z's and y's or whatever combination using x's and y's, you could generate cylinders and spheres and all sorts of three-dimensional shapes. For every single point in that blob, we associate a value f of x, y, z. So I want you to imagine that f of x, y, z is telling you the temperature of any point in that blob. So when you calculate a triple integral, You are not getting the volume of that blob. What you are getting is the total amount of whatever that is. Imagine that's heat, right? You're getting the total amount of heat in that blob. If this would represents the electric charge at any point x, y, z, right? If this function told you what the electric charge at this point was and at that point is, the triple integral is telling you the total amount of charge in that ball, right? So it's basically adding up some property described by this function of every point in the blob. Now, if you wanted to know the volume of a blob, all you do is make the function the number 1. So if every point on the thing it's called 1, adding it all up is basically adding its volume. And so you'll get the volume of the shape. So if this shape here was, say, a region R, this would be the volume of R. But typically, triple integrals are only adding up all the values in a 3-dimensional solid shape together. Now, if you think that's bad enough to describe, you can actually get, I don't even think they call them this, but quadruple integrals, 4 integrals, right? An integral, an integral, an integral. Now, when you reach that point, forget about trying to visualize it. It doesn't work anymore, right? You're into dimensions where all you're thinking of is that this thing is adding up something in multi-dimensional space, right? It's finding a property, it'll be called f, x, y, z, w probably, and it's adding up all the points in some region in 4-dimensional space. So we'll start today with the easier ones, which are ones where the regions are pretty well defined. So not unusual to start at question 1 then. The integral, the triple integral is written like that. The function that we're going to deal with is this guy, and it's going to be a dv. And the region B is described like this. X is 0 to 1. Y goes from -1 to 9. And Z goes from 0 to 4. Well, I got everything I need. In no particular order, X is going to go from 0 to 1. The limits of Y are going to go from -1 to 9. And the limits of Z are going to go from 0 to 4. Do you see in these questions, X, Y, and Z are treated exactly the same? You know, in the previous questions, you had to rearrange things so Z was a function of it. No, not in this particular way of doing things. Each one is considered independent of the others. Now, the function that we've got is x, y, z squared. And since the order I've set it up is going to be dz, dy, dx, that's what the triple integral is now becoming. Now, when we did dA, the reason we did dA is don't sometimes x's and y's work, but sometimes polar works. When we call a guy dv, as we are here, that's because x, y, z works, right? But in the future, we will be able to do polar versions of x, y, z, or cylindrical, as they're called, that's basically polar, or spherical coordinates, which is even weirder, but that's not any time in the next week. So we got these guys. Let's look at making life easy. If all the limits of integration are numbers, and the function is x, y, z squared, would you agree that this is a variable separable situation? So I can break it into the integral from 0 to 1 of x times the integral from -1 to 9 of y times the integral of 0 to 4 of z squared, and that's a dz, and that's a dy. And when you can do that, you should, because it's going to make your life 100 times easier than if you just do it the old-fashioned way. So this guy is 1/2 x squared evaluated at 0 to 1. This guy is 1/2 y squared, evaluated at -1 to 9. And this guy is 1/3 z cubed, evaluated at z equals 0 to z equals 4. Right, you plug this guy in, eventually you get a half. What are you going to get? You're going to get 81 halves. Take away 1, so you're going to get 80 halves, so that's 40. And this one, you're going to get 64 thirds. And that'll cancel down to 20, so you're going to get a 0, 8, 1280 over 3, and that would be your answer. All the limits of integration were numbers. What I want to do now is look at a triple integral where at least one of them, in this case the z's, contain variables. So you're going to have your region and this fella here, and let's suppose that what we have is just x, y, z, and it's going to be a dz followed by a dy followed by a dx. Are we good with the setup, right? So this is your question. So what I'm going to do is essentially integrate that. Now you might say, wait a minute, I can variable separable that. Well, no, you can't anymore. If the limits of integration contain any kind of variable, you cannot do variable separable, right? You just have to do them one at a time. So this fella is going to be from 0 to 1. This fella is going to be from 0 to 2. And if you integrate x, y, z with respect to z, you get 1/2 x, y, z squared, evaluated at z equals x to z equals y squared. So I've integrated that with respect to z, and here's my limits. Let's see where this leads to. You plug the z for y squared, and this fella becomes 1/2 x, y, y to the 4, so y to the 5. Take away, you make an x in here, and you get minus 1/2 x squared, so that's what x cubed y dy dx. Now, unfortunately, we didn't get it, but can you imagine in a different world, this here was variable separable? Because these are numbers and these are numbers, then I would separate it out. But there's no easy way to separate this out. You'd still have x's and y's left over. So I'm just going to move on and now integrate this fella with respect to y. So you're going to add 1 to the power, divide by the new power, and that's the first one. Add 1 to the power, and then divide by the new power, that's the second one. And evaluate it at 0 and at 2. If you plug in 2 here, you get 2, 4, 8, 64. 64 over 12 gets you 32 over 6, gets you 6. Oh, yeah. 2, 4, 8, 16, 32, 64, 12. So I'm not going to simplify it. I'll do it later. That guy. Plug in 2 here. Oh, you get 4, which cancels out nice. So you get that guy. Take away a whole load of zeros, so it doesn't matter. And now you have one more integral with respect to x, which is this guy. Where did that y squared come from? That y squared is not there. 4 and 4 cancels, just x cubed. So that guy, divide by 2. We get this guy. Power rule for this guy. Evaluated at 0 and at 1. Well, that's actually quite nice. You're going to get 64 24ths. Take away a quarter. Minus a whole load of zeros. That's going to get me 6 24ths, which is going to get me 58 24ths. And that's going to get me 29 12ths. Okay, I finally got an answer. So if one of your limits of integration contains variables, You can't do variables separable. You just integrate with respect to whatever this variable is, and then the next variable, and then finally x's in this case. Any questions about that? Triple integrals. Okay. Let's move on then and do the next level. So I did a triple integral where everybody was numbers. I did a triple integral where only one of them had a variable. The next one is question 3. And the triple integral this time is z equals 1 to 3, x equals 0 to 2z, and y equals 0 to the natural log of x. And the function is x e to the negative y dy dx dz. Of course, when you get web assigns, they don't tell you the y, they don't tell you that's x, and they don't tell you that z. The clue is dy makes this guy y, dx makes the middle one the limit of x's, and dz tells me the outside one. If you're doing any triple integral, the last integral, right, the outside one must be numbers, or else the question doesn't make sense. So you know the worst case scenario is going to be this one, where both two variables contain x's and y's. So I'm not going to do anything about that, and I'm not going to do anything about that. What I am going to focus on is that guy. Well, with respect to y, right, if you integrate this expression with respect to y, you will get x e to the negative y with an extra negative. Are you all happy where that extra negative came from? Okay. Evaluated at y equals 0 and y equals natural log of x. Plug in the y, replace it in here, you get negative the natural log of x. And that's the first guy. Take away negative x e to the 0. And then you're going to do a dx and finally a dz. Style points is always our friend. And so I should try and make this much nicer. And I'll do this on the side. Negative x e to the natural log of that guy looks really ugly. Well, it is really ugly, but it ends up being not anywhere near as bad as it is, because it's actually the same thing as that guy. And we all know that e to the log x is x, and so the answer is negative 1. You could also do it this way. E to the negative log x is e to the natural log of x to the power of negative 1, which is negative x e to the natural log of 1 over x, and then e a natural log gets you that guy, which also gets you negative 1. So whatever approach, it's negative 1. So this guy is negative 1. Take away a negative is add. E to the 0 is 1, so you basically add x, and now you can do a double integral. So triple integral, once you've done one of the limits of integration variable, now turns into a double. This one is not separable, you've got letters there. So I don't care about this guy yet. What I do care about is that guy. Well, if you integrate this with respect to x, you get negative x plus 1/2 x squared, evaluated at x equals 0 to x equals 2z. Okay, you plug 2z in here, you get negative 2z. You plug 2z in here, you get 4z squared, but half of 4z gets me plus 2z squared. Then you take away a load of zeros, so we don't care about that. And now we get to that stage. And at this stage, isn't that just Calc 2? You can do the power rule and you'll get your answer. So, triple integral with 2 of the limits of integration containing variables. A triple integral where one of the limits of integration contains a variable. And although I can't find it, here we go. And a triple integral where everybody is a number. So that's pretty much all the permutations if you are given the integral written in this format, right? So that's kind of where we're going to, the type of question we're going to stick to today. So let's do a version of 5. We're asked to find a triple integral over some region E, and the function is y dv. And E is basically, I'm just going to write down what it says. It's that guy, that guy, that guy. Now we have a decision to make here. It may not seem obvious, but there is something that we have to do and it has to be done properly. And that is we have to decide the order in which to set up the triple integral. Now, since that's got numbers, the numbers always go to the end. Now, I have two choices. This middle one can be y equals 0 to x, or this middle one could be z equals here to here. Only one of them actually works. Only one of them does the job. Which one should go in the middle?
I'll take a guess. I think, I guess Y should go in the middle.
I agree with you. And since you've never been shown this, that's a pretty good guess. Essentially, you always go from ugliest to less ugly to numbers. So can you see this one is pretty ugly because it actually contains 2 of the variables, right? It contains x's and y's. This one only contains the x's and this one only contains the numbers. So if you've got a limit of integration, you've got 3 choices, the x, the y, or the z. The ugliest one always goes first. The ugliest one to me means the one with all the variables in it. You see how this has got x's and y's in it and z's, right? It's got all the variables in it. Make that one go there. The numbers have to go at the end, and whoever's left goes in the middle. So that's maybe the simplest way to think of it. Now in this case, dz, dy, dx. Right, I'm not going to do all of this one. Let's just do one piece of it just to get into the swing of things. That's going to be the guy I'm doing first. So I don't pay too much attention to these two right now.
For that
If
one,
you question,
when you're going off of 5, is it z equals negative or z equals x minus y, or are you just doing your own?
I'm just doing my own.
Okay, just making sure.
So in this case here, we have integrate this with respect to z is actually not that bad, isn't it? Just xz evaluated at negative y and x plus y. And that gets us x equals 0 to x equals 4, y equals 0 to y equals x. Right. If you plug x plus y for z, you get y, x plus y. Take away y times negative y, which is negative y squared, dy dx. Let's see what we get now. X equals 0 to x equals 4, y equals 0 to y equals x. Xy plus y squared plus another y squared. So that's basically going to be xy plus 2y squared. Right, can you see that that's now a pretty standard double integral when you do your thing? So think of triple integrals, at least in the format that we're looking at right now, as just really like the same process as a double integral, but with one extra level that we need to take care of, right? In this case, that would be the extra level. And actually, fourth and fifth and whatever level of integrals you want are really just repeating the process all the way down from 5 integrals to 4 to get you 3 to get you 2 to get you 1, and then you're finished. So theoretically, at least, we could do any level of integration that we want. Are we good? Any issues?
No issues here.
In the big scheme of things, is this a little bit easier because if you think of it as just a extension of what you do with double integrals, the math is very, very similar, they're just more of it.
It means more eraser.
Okay, that is probably true. The next question, well, let me show you what they have. They even have the answer, which I kind of like because it means when I do a question, I can check that it's right. Okay. They ask you to evaluate this integral with respect to z, then this double integral with respect to z and y, and it's all building up to this one. So that guy there and that guy there is really just a working that you would use. In a way, that's very distracting from me. So I'm going to just set up the x's, go from 0 to 2. The y's go from 0 to x. And the z's go from x minus y. Well, that one might be the one that you were thinking of earlier. I think it was Sarah, right? Right, so when we're finished, the answer better be 8/3. So let's see the story. Oh, and the guy that we're integrating over this region, what they're calling it this time, they're calling it E, they can call it any letter they like, it's that guy. And the function is just y dv. It is virtually, actually, it is virtually a carbon copy of the previous question 5. Okay. So I'll just set up this integral, but I don't intend to do it much further than that because it's so similar to an earlier one. So I need to figure out, just like before, who goes here, who goes in the middle, goes at the end. The x's contain the numbers, so they can go there. Would you agree the z's the ugliest and the y is less ugly? So in this case, z is going to go from x minus y to x plus y, and the y's are going to go from 0 to x, and then it's going to be a dz dy dx, and that is the triple integral now set up. And it's almost exactly the same as the one I did a few minutes ago. So if you focus on that guy, can you see you're going to get yz again, and you plug in some numbers. I think in this case it might end up being a little bit simpler, but not much. Then you do it with y's with those numbers, and then finally with x's. Let's see if I can find one. Yeah. It's time. Right, I'm just scanning through the ones, and every one I'm looking at is going to take a heck of a lot of time to do. But no, it's just going to take too long myself. See if I can find a quick one. Okay, how about this one? This one I think's quick. I might not know it until I start it. So in this question, you're given a tetrahedron 10x plus 4y plus z equals 20. Right. And we have to use this triple integral to find the volume of the tetrahedron. Now we know how to do volumes. It's a triple integral of 1. Okay. What we don't have is the limits of integration, right? X from here to here, Y from here to here, Z from here to here. So let's build that from scratch. So if you ever want to find the volume of a shape, let's call this region E, right? If you want to find the volume of a region E, you do a triple integral of 1, and that will get you the volume. Right, in this shape here, right, if you make those two guys 0, you get 20 here. If you make those two 0, you get 5. And if you make those two zeros, you get 2. So essentially the tetrahedron they're talking about is this guy here. Can you imagine it's like a little bit of a pyramid guy? So far, so good. I need to find the range of x's, the range of y's, and the range of z's, because that's what's going to go here. When I look at this shape, what I see on the ground is a little triangle. So I'm going to orientate it like this. And I'm going to make that 2. And I'm going to make that 5. And I'm getting deja vu here because that's almost exactly the same as one of the earlier triangles we got, isn't it? Now, let's talk about the z's. If you look at this triangular plate here, that's this fella. If you rearrange this fella, you get z equals 20, take away 10x, take away 4y. So that's one of the z values. So I can imagine a point here dropping down to there. That would be a typical vertical line from the surface to the ground. What is the z coordinates of the point on the ground, the one that's touching this triangle? What's its z value?
A goose egg.
Correct. Isn't it the floor? Z. Now, this guy here is going to tell me who x's and y's are. Well, it's a straight line, and I'm going to go vertical, because I like vertical. And so on x go from 0 to 2. And then I need the equation of that line, and the slope of that line is -5/2. That's why I think it's almost identical to one I did earlier. So it's -5/2 x add 5. So we're going to have y going from 0 to -5/2 x add 5. That represents your region, what have I called it, E. The z goes from the floor to the slope. The y's go from the bottom of the triangle to the line, and the x's go from 0 to 2. And we have pretty much done as much as I want to do. I'll just finish by setting up our triple integral of 1. Okay, let's call them things. Let's call them A, B, C. Which one goes right next to the one, the innermost limit? A, B, or C? What goes here? What limits of integration go there?
The ugly one.
Okay, and the ugly one is definitely the Z, C. So Z goes from here to that guy. Would you agree that the next ugly guy is B? And X goes from 0 to 2. And when you evaluate that guy, you will have found the volume of that tetrahedron, right? I mean, if I draw that tetrahedron in a slightly different orientation, it kind of looks like this guy. You see, it looks like one of those funny little dice that you get that has 4 numbers on it. And I think that's a nice natural point for us to stop. When I see you on Wednesday, we'll we'll finish off the rest of triple integrals as far as we need to. And then whatever time we've got left, we can throw that open, John, to try and go over anything you might want to talk about for your midterm. But the general things are going to be true, right? Just like in the final. The only things that you can have in front of you are things that you have printed, right? Notes that you've got, unit circles. I'll keep online the standard integrals unless you want to print your own. They take a lot of paper if you do that. And no WebAssign will exist. Everything will disappear. Everything else on Canvas will disappear, and you are not allowed to use anything else apart from your calculator, which is pretty standard rules. Okay, any questions before we call it a day then?
Are we going to have an exam this week along with the midterm?
Yeah, the
Okay.
exam is the usual one, finished by midnight Sunday.
Okay.
In a kind of nice way, I don't know if you'll agree with me, but in a kind of nice way, isn't that one going to be the freshest in your mind? So you might want to think about, you don't need to revise on that one because you've been doing it today and Wednesday. The ones you're probably going to have to spend more time thinking about over the next few days is like week 1, 2, 3, 4, right? Those weeks, which are a little bit now in the distance. If you did catch it, I do have on Canvas some resources where I've given you some questions and their solutions. So hopefully that'll be an aid to reminding you how to do certain things.
Okay, thank you.
You're welcome. Okay, any other questions or are we good for today?